Hey, welcome. This is YourAlly AI. Today we are designing a batch inference system, the kind of problem that shows up across big tech, especially at places like Anthropic, OpenAI, XAI, Google, Meta's intelligence labs, and a lot of other ML platforms. Picture this: you open an app, type a message, hit send. A couple of seconds later, an answer shows up. It feels effortless. On the other side of that button, somebody still has to place real GPU compute behind every request at huge scale without lighting money on fire and without making paying customers wait behind a free tier stampede. The naive idea sounds clean. Give every user their own GPU, one request, one processor, answer immediately, isolation for free. Then do the cost check. A high end cloud GPU is a few dollars an hour. Multiply by tens of thousands of concurrent users, and you're explaining a budget to a very quiet room. So we share GPUs, and the moment we share them, we have to batch. But here's the twist that makes this interview hard. The client still wants a normal synchronous experience. They post, they wait, they get a response on the same connection. They should never know botching happened. Interactive chat and this design can share models and even a cluster. But success looks different. Chat cares about streaming feel. This problem cares about packing GPUs while still answering under a hard P95 on the same HTTP connection. That's today's problem. By the end, you should walk FR1, FR2, FR3, draw gateway to GPU, and defend when the batcher fires, and how each answer finds the right person, without sounding like you memorized a blog. If you've only practiced URL shorteners, same muscles. Clarify, interface, bottleneck, trade offs. The bottleneck just wears a GPU this time. Let's lock requirements. Let me slow down on the cost story because this is where interviews get real. Suppose a GPU is $3 an hour. 1,000 lonely GPUs for 1,000 concurrent chats is $3,000 an hour before you sold a token of value. That's not a platform, that's a charity for silicon. Batching is how you turn that into a business. Fill the GPU with many requests that can share the same weight load and the same kernel time. One promise for the next sections. Every major claim gets a diagram. Requirements board, end-to-end flow, sequence, wrong versus correct twice. Option C. You're not here to collect vibes. You're here to leave with pictures you can redraw. Next section, requirements. In this section, we lock what the interviewer usually gives you and what you should write on the board before drawing boxes. Functional first. FR1 synchronous request. Client sends a post, waits and gets the response on the same connection. No, here's a job I'd come back later for the happy path in this problem family. FR2 internal batching. Requests get grouped invisibly. The client never sees a batch ID. If you say that out loud, you already sound organized. FR3 tier based priority, enterprise first, paid second, free users get said under load. That's how paying customers still feel the product when traffic spikes. Non functional, keep it sharp. NFR1 P95 latency under about 500 milliseconds end to end. That number is why wait until the batch is full will get you killed when traffic is quiet. Now the constraints interviewers often hand you. Constraint 1, one batch at a time per GPU. Constraint 2, inside a batch, everything runs in parallel. Constraint 3, staff level, positional identity. Inputs at slot I produce outputs at slot I. No fancy routing logic on the GPU. And the economic insight, one request or 100 requests can cost roughly the same GPU time. Batch to maximize output per dollar. without blowing the P95. Candidates who only talk latency sound incomplete. Candidates who only talk cost sound cold. Tie them together. How you'd open in the room. I'm assuming synchronous post semantics, invisible server side batching, 3 priority tiers, and a P95 under 500 milliseconds. Does that match? That sentence buys trust. If they change a constraint, you adapt. Don't marry your first diagram. Also name what you're not solving yet. Multi-region, exact kernels, training, scope control is part of the answer. Write those down. Then we design APIs that honor them. Let's make FR1 visceral. The browser is holding a connection open. Nothing comes back until the server finishes. Multiply by 10,000 people hitting send together. That's the starting pressure. FR2 is the magic trick. From the client's point of view, this is still one request and one response. From the system's point of view, that request might ride with 99 strangers for a few dozen milliseconds. FR3 is politics encoded as queues. Under load, free traffic gets said so enterprise stays fast. If you can't say that without flinching, practice it. Interviewers will. On positional identity, think of the batch as a train with numbered seats. Seat three's answer must return to seat three's passenger. The GPU doesn't need name tags if nobody rearranges the seats. Economic card again. If the batch's wall clock is roughly fixed, empty seats are burned money. Fill seats carefully under the latency ceiling. Last beat on requirements. Write a one-line success statement. Under P95, 500 milliseconds. Return sync inference results while batching on the server and respecting enterprise over free priority. If your design can't say that sentence, keep clarifying. If the interviewer withholds numbers, propose them. P95, 500 milliseconds, 3 tiers, marks batch 100, timeout around 40 milliseconds. Label proposals, beat blank silence. Next section, APIs and entities. APIs and entities. Keep this boring in a hireable way. Core pieces on the board. A request with rec ID, input, model, max tokens, and tier. A future. The parked HTTP connection waiting for a result. Tier queues, enterprise, paid, free, a batch, ordered list of requests, a GPU worker that runs one batch at a time. API shape post slash v1 slash inference with the input payload. Gateway checks auth, resolves tier, rate limits. If the system is full, return 429. Don't silently queue forever and miss the SLO. Critical line for FR1. The connection stays open. You park a future. You do not close the socket and ask the client to poll. Once you hang up, that HTTP conversation is gone. Then enqueue into the right tier queue. The batcher is invisible to the client. FR2 doing its job. Separate queues give O of one priority without scanning a megastack. Walk a tiny example. Paid user sends what is Paris model LMB1 max tokens 100. Gateway stamps tier paid, creates future F, pushes to queue paid. The TCP connection sits there politely while the factory works. Entity tip, model revision immutable on the request. Latest as a moving target is how you debug ghost at 3 a.m. Cancel and disconnect. If the client vanishes, resolve the future cancelled and let the batcher drop waiterless work when safe. You don't need a novel. You need to show abandoned connections crossed your mind. Trap. Designing only a streaming chat endpoint with no park, no queue, no batch path, cool demo, wrong interview. Entities locked, quick pause to practice, then math. Spell the future idea for humans. A future is a promise object tied to a socket. When the GPU answer arrives, you complete the promise and the HTTP stack finally writes bytes to that waiting client. Why tier fields belong on the request entity. The batcher shouldn't reauth. Auth once at the edge, stamp the tier, pass a small envelope downstream. Idempotency for retries. If the gateway times out and the client retries, a rec-id lets you avoid double billing or double enqueue chaos. Mention it once. What strong candidates write for status on the wire, success with output, or structured error with retriable flag. Don't invent 7 custom enums under time pressure. Interface summary you'd leave on the board. Post inference, park, enqueue by tier, batch internally, demo by position, respond on the same connection. One more interface detail worth ink. The gateway should accept a client timeout or use a server max wait aligned to P95. If the future is not resolved in time, return a clear gateway timeout and make sure the batcher can notice cancelled waiters. Dangling compute is how clouds get interesting invoices. Security note: without a TED talk, prompts and outputs may be sensitive. Tenant isolation in object logs and queue payloads matters. Stamp tenant ID early. Board hygiene: draw the future next to the gateway, not next to the GPU. Identity and waiting: live at the edge of the user's connection. Quick pause. If you want to practice this live, mocks, system design loops, FR1 through FR3 under a clock, sign up on YourAlly AI at yourally.live. Watching is useful. Saying it out loud is a different sport. About 30 seconds of product so you can see the path. Alright, back. Let's size the fleet. Back of envelope. Interviewers don't need perfect flops. They need a method you can recompute when they change the numbers. Start with demand, say 10,000 QPS at peak. Translate into work a GPU can finish under batching. Per GPU effective rate, batches per second or tokens per second with healthy packing. Label assumptions. Utilization is not 100%. Say 70 to 85 and why: packing gaps, warm-ups, retries, bad deploys on Fridays. Fleet size is demand divided by effective capacity plus headroom. Cost is dollars per GPU hour turned into dollars per million tokens. Concrete sketch. Peak 10,000 requests per second. Suppose a GPU finishes a packed batch in about 100 milliseconds. Roughly 10 batches per second before the utilization haircut. At 75% utilization, you're in the ballpark of needing on the order of 1,000 plus GPUs at peak before headroom. Then adjust live with their rates. Wrong numbers beat no numbers. Correctable numbers beat confident nonsense. Bridge to design: the 40 millisecond batcher timeout must fit inside the 500 millisecond P95 along with queue wait, GPU time, and network. If your timeout is 200, you've spent a huge slice of the SLO before the GPU starts. That bridge is the interview signal. Next, high level design, boxes with intent. Another angle: latency budget partitioning, 500 milliseconds total. Give yourself a mental pie: network, gateway, queue, wait, batcher wait, GPU, demo. The batcher timeout is only one slice. If queue wait dominates, you need more GPUs or better setting of free tier, not a smaller batch timeout. Diagnose before you tune. Utilization honesty: a dashboard at 99% often means you're about to miss SLOs. Leave headroom on purpose and say so. Cost interview probe: show dollars per million tokens before and after raising batch size. Even a back of envelope delta shows you think like a platform owner. Final math habit: always show the utilization factor as a labeled assumption. Interviewers will tweak it. you want to look flexible, not fragile. If they give you GPU tokens per second instead of batches per second, convert. Same method, different unit. Flexibility is the flex. Next section, high level design. High level design, walk the board left to right, FR1, FR2 and FR3 in one picture. Clients A, B and C hit send. Traffic hits a load balancer, then the API gateway. Auth and tier live here. If you're full, for 29. And right here is FR1. Sync hold, keep the HTTP connection open while work happens behind the scenes. From the gateway, request FAANG into tier. Queues, enterprise, paid, free. That's FR3 made physical. Separate queues give constant time priority without scanning a giant list. Free can be set under load without starving enterprise. The request batcher polls by priority. It aggregates until a size limit, often 100 or a timeout floor, often around 40 milliseconds. That's FR2 batch aggregation the client never sees. Dispatch into a GPU worker pool, one batch at a time per GPU inside the batch parallel. Don't draw 20 GPU microservices, draw a pool with a clear scheduling rule. Bottom of the board, a response handler. Outputs I maps to future I, wakes the parked socket, completes HTTP. That arrow back to the client closes FR1. Sad path, 30 seconds. Worker dies mid-batch. Heartbeats stop. Futures can't hang forever. Timeout and retry with stable request IDs or fail fast if retries are exhausted. The open connection still needs success, retriable error or failure. Overdraw trap is service per noun. Underdraw trap 150 and a shrug about enterprise. Point at FR labels as you talk so the picture and the requirements share vocabulary. If you can redraw this calmly, you're ahead. Next, the sequence up close. Zoom on the gateway box. It is the policy brain for admits, auth, tier, rate limits, for 29 when full. Keep model weights out of this box. Zoom on queues. 3 lists beat 1 priority heap for this interview. Simpler op story, clear setting story, clear metrics per tier. Zoom on the batcher. It is not a generic worker. Its job is packing under time and size constraints, then speaking GPU dialect, dense tensors, not HTTP. Zoom on the response handler. This is where identity returns. If you accidentally put demux on the GPU, you've already failed deep dive B in advance. Offer the interviewer a steering wheel. I can deep dive batcher firing, demo, or scale out next, which helps most. Collaborative beats steamrolling. Let me give you the 1 minute tour you'd actually say while pointing. Clients hit the load balancer, gateway authenticates, stamps tier, and parks the HTTP connection, that's FR1, VNQ into enterprise, paid, or free lists, FR3. The batcher polls in that order and builds a batch until we hit max size or the timeout, FR2. We dispatch to a GPU that runs one batch at a time with parallel slots inside. Results come back in order. We resolve futures and complete the original connections. That paragraph is the spine. Everything else is ligament. Common interviewer push. What if enterprise and free share a GPU? Answer. They can share silicon. They should not share fate in the queue. Priority is about admit and wait, not necessarily physical isolation, unless compliance demands dedicated pools, which you then price in utilization loss. Another push, where is the model cache? Warm weights on workers matter. Sticky routing to warm models is a fair bonus. Don't let it hijack the main story. Auto scaling sits beside this picture, not inside the batcher. Scale GPUs on queue depth and P95. Scale batchers on control plane CPU. Different knobs. Before we leave the high level board, Tap each FR label one more time. Sync hold. Invisible batch. Tier priority. If a box on your diagram does not serve one of those, ask why it exists in Toad. API data flows 6 steps: lifelines, client, gateway, Redis style queue, batcher, GPU worker. Step 1: client posts, inference, input, model, max tokens. Step 2: gateway validates, auth, OK, tier paid, rate limit pass, parks the future, connection stays open. This is the moment most candidates forget and accidentally design polling. Step 3: gateway RPUs into queue paid or ent or free. QAC case, tier separation is how FR3 stays O of 1. Step 4: batcher atomically moves work into a processing list. Think bar pop elpos style so a crash doesn't lose the request into a black hole. Accumulate until size 100 or 40 milliseconds. Step 5: batcher posts one internal batch to the GPU. Ordered request, GPU locks for that batch. Slot E maps to work for input I. Fixed is batch time is the economic punchline. Step 6: GPU returns results in the same order. Batcher demuxes by position and resolves each future. Client gets HTTP 200. Technical punches without a vendor sermon. Separate tier lists, atomic processing move. GPU never sees the queue, only a dense batch. If they ask Kafka versus Redis, defend properties. Fast pop, durability needs, ops complexity, then pick. Callout rail, parked socket, tier queues, size or timeout, one batch per GPU, demux by position. Tell it as a story, not a grocery list. Deep dives next, replay step 2 slowly, validate, create future, do not close. If you close, you force the client into a job API you never designed. Replay step 4, atomic claim matters. At least once with idempotent request IDs is usually enough. Exactly once marketing language is a trap. Replay step 5. The payload is an ordered array. That order is a contract with deep dive B. Break the order and demux becomes fiction. Observability hooks, log rake ID at gateway, batch ID at batcher, GPU worker ID, and queue weight histograms by tier. Those four explain most incidents. If time is short in the real interview, narrate steps 1, 2, 5, and 6 first. Park batch return. Then fill queue details if they ask. I want you to hear the timing. Gateway work should be microseconds to low milliseconds. NQ is fast. The wait is either batcher fill time or GPU time. If your traces show gateway as the long pole, you overbuilt the wrong box. On BR pop pulpus style claiming, the property you want is exactly one consumer owns this message while processing. If the batcher dies, a reclaimer requeues from the processing list after a visibility timeout. That's ops literacy. On the internal batch, post include batch ID, ordered request, and model revision. Keep it boring JSON or protobuf. The contract is order. Return path. Do not stream tokens in this problem unless they ask. Sync completion matches FR1 as stated. Streaming is a different chapter of product. End the sequence section by tapping the callouts. Parked socket, tier queues, size or timeout, one batch per GPU, demo by position. If those 5 stick, the deep dives will feel inevitable instead of random. Last habit on sequences, number the steps out loud as you draw. Interviewers follow numbered stories. Unnumbered arrows become spaghetti. Next section, deep dives. Deep dive A. When exactly should the batcher fire? Wrong instinct, fire only when the buffer is full. At 10,000 RPS, a batch of 100 fills in about 10 milliseconds. Looks fine. At 3 am with 5 RPS, the first user waits roughly 20 seconds for 99 friends who are asleep. That destroys P95 unacceptable. Correct, fire on either condition. Hit 100 GPU full, great, or about 40 milliseconds since the first request in the buffer, timeout floor, whichever comes first. Why 40, not 5 or 200? 5 milliseconds makes tiny batches, waste GPU, raise cost per request. 200 helps utilization, but users feel delay when traffic is thin. Around 40 is a common sweet spot that keeps P95 under 500 milliseconds while still building meaningful batches. At high load, size hits first anyway. Timeout is the quiet hour safety net. Worked contrast, high load, size wins, util looks great. Low load, timeout saves the lonely user. One policy, two regimes. If product wants tighter P95, shrink timeout, accept smaller batches, and say the cost trade-off out loud. Staff answers negotiate. Optional probe, shorter timeout for enterprise than free, maybe, same mechanism, product knobs on top. Interview line, size or timeout, timeout derived from the latency SLO. Draw the two triggers as an OR gate on the board. Size path, time path. Meeting either fires, missing both forever is the bug. Metrics that prove the policy works: batch size histogram, time to fire histogram, and P95 by tier. If nighttime P95 spikes, your timeout is too high or your free tier is flooding. Anti-pattern, adaptive magic timeout with no explanation. Prefer a simple constant first, then adaptation as a later knob. Connect back to economics, larger max batch raises util, longer timeout raises util at low QPS but hurts lonely users. The OR gate is how you stop choosing only one side. Practice sentence. Full buffer only fails at low traffic. Size or timeout covers both day and night. Let's put numbers on the loneliness problem. 5 requests per second, batch size 100, time to fill is about 20 seconds if you wait for full. Your NFR was 500 milliseconds. You are now 40 times over budget before the GPU starts. That is the wrong instinct with math. Flip to the OR gate. At 5 RPS, 40 milliseconds collects maybe 0 extra frames. You still fire a tiny batch. Util dips. Latency lives, product survives the night. At 10,000 RPS, 100 seats fill in 10 milliseconds. Timeout rarely wakes. Util thrives. Same code path. How to choose 40? Start from P95 budget, subtract GPU time and network and queue. Leave a residual for batching delay, pick a timeout near that residual, then validate with a histogram in staging. Say the method even if your constant differs. Enterprise variant, maybe 20 milliseconds timeout for ent queue and 40 for paid. Mechanism unchanged. Configuration carries policy. Remember the title of this deep dive as a question you ask yourself on the board. When do we fire? If your answer is only when full, erase it. Write size or time, then derive time from the SLO. That alone separates senior from staff on this prompt. Deep dive B. How does each answer reach the right person? Wrong instinct. Tag every GPU output with a request ID, then search. The GPU parses structures and jumps around in memory. Non-coalesced excess. You can lose an order of magnitude. Parallelism dies, expensive paperweight. Correct positional identity. Outputs I is always the result for inputs, i.e., position is identity. No parse, no lookup on the device. Before firing, snapshot an index map atomically, 0 to future A, 1 to future B, and so on. Arrivals after the snapshot go to the next batch. Demo stays deterministic and race free. After return, for I output in enumerate outputs, index map, I resolve output. Each resolve wakes a parked socket. HTTP completes. Why coalescing matters? Adjacent threads want adjacent memory. String IDs scatter reads. Dense arrays keep hardware honest. Clean split, batcher owns identity, and HTTP GPU owns math. Crossing those wires is how designs get clever and slow. If one slot errors, preserve positions, mark failed at that index without shifting the array. Order is sacred. Interview line, ordering stays on the batcher. The GPU only sees dense arrays. Whiteboard the wrong path. GPU returns JSON with IDs. Host scans for matches. Threads diverge. Say non-coalesced out loud. Interviewers in ML infra listen for it. Whiteboard the right path. Two arrays, same length, same order. Host loop is trivial on purpose. Trivial is good when it runs a million times a second. Race example, request arrives while you are flushing a batch. If you append into the live batch after snapshot, index maps lie. Snapshot boundary is the lock without a lock. Parcel failure, slot 7 ohms or content filters. Keep length n, status array or sentinel output. Never delete slot 7 and shift 8 left. Practice sentence, position is identity, the batcher snapshots futures before fire. Resolve by enumerate. A concrete failure story, a team tags outputs with IDs to be safe. Throughput collapses under load. Profiler shows gather, scatter on the device. They fix it with more GPUs. Bill goes up. Root cause was identity in the wrong layer. Positional design is not laziness. It is aligning software with how SIMT hardware wants to run. Index map snapshot. Think of it as closing the airplane door. Anyone late boards the next flight. Mixing late passengers into a closed flight's seat map is how you hand the wrong bug to the wrong human. Resolve loop belongs on a fast host path. It should be boring code you could write half asleep. If your demo needs a distributed lock, you have overcomplicated identity. Tie to FR1. Resolving a future is literally how the parked HTTP connection finally moves. Demo is not bookkeeping, it is user experience. Remember this deep dive as a question. How does each answer reach the right person? If your answer involves the GPU parsing IDs, erase it. Right position is identity. Then show the index map snapshot. That pair of moves is the wow moment in a lot of real loops. Deep dive C is scaling the control path. When one batcher becomes the bottleneck, people invent shared queues with locks. That works until latency, jitter, and incident channels show up. Quick map, option A, single global queue, simple hot lock, noisy neighbors. Option B, shared batcher fleet fighting over one buffer, coordination tax. Option C, recommended partition at the gateway. Hash request id mod n at the API gateway. Send each request to a batcher with its own local buffer. No shared hot queue, no lock on the admit path. Each batcher owns a non-overlapping slice of request space. They still dispatch into a shared GPU pool. GPUs are expensive, keep them utilized across partitions. Caveat you'd admit, when n changes, rebalancing needs care, sticky hashing, and gradual drains help. Saying the caveat is credibility. Interview line, eliminate shared batcher state with consistent hashing at the gateway. Keep the GPU pool shared. Deep dive set done. One more practice beat, then recap. Why gateway hashing? The edge already touches every request. That's the natural place to shard without a central batcher lock. Local buffer means each batcher can run the same size or timeout logic independently. You scale the control plane horizontally. Shared GPU pool means you still park expensive devices. Don't dedicate GPUs per batcher unless isolation requirements force it, and then admit the util hit. Failure mode, one batcher hotkey if rec eds are adversarial, use a proper hash, monitor per partition QPS, split n if skewed. Practice sentence hash at gateway to batch or local buffers, share GPUs, avoid shared admit locks. When do you reach for option C? When batch or CPU or lock contention shows up in profiles while GPUs are still hungry. Don't partition because a blog said so. Partition because the control plane is the bottleneck. Consistent hashing detail, use rec ID or a stable hash key. Avoid hashing on raw prompt text. You want balance, not accidental stickiness on popular prompts unless intentional. Local buffer plus shared GPU. Batches compete for GPUs with a simple lease or work queue into the pool. That second queue is okay. It is behind packing, not before priority. Compare in one breath for the interviewer. Global queue is simple and contains shared buffer coordinates, partitioned admit scales. I recommend partitioned admit. Close deep dives, firing policy, positional demo, partitioned admit. Those three are the staff trifecta for this question. Remember option C as the scale story. When the batcher path hurts, shard admit at the gateway, keep GPUs shared. You are not required to implement consistent hashing on the whiteboard. You are required to show you know where coordination dies. Before recap, if you want to pressure test this under a live mock, your Ally AI is at yourally.live. System design reps beat passive watching, 30 seconds of product. Okay, recap. Final section recap. Screenshot this mentally. FR1 Sync hold, FR2 Invisible batching, FR3 Tier priority, P95 under about 500 milliseconds. One batch per GPU, parallel inside the batch. Positional identity. Outputs I for inputs I. Path. Gateway. Tier queues. Batcher with size or timeout. GPU pool. Demux back to parked connections. Wrong. Wait for a full buffer. Correct 100 or about 40 milliseconds. Wrong. Request IDs on the GPU. Correct position is identity. Scale. Partition at the gateway. Option C. Share the GPUs. 30-second close. Clarify sync hold. Invisible batching. Tiers and P95. Design park plus tier queues plus batcher. Fire on size or timeout. Demo by position. Partition at the gateway when the control path scales. If you can tell that story calmly, you're in staff territory for this question. Practice live mocks and system design loops on your Ally AI at yourally.live. Thanks for hanging through the queues and the GPUs. Go design something that doesn't set money on fire and still answers in under half a second. We'll see you on yourally.live. If you remember only three diagrams, requirements board, end-to-end flow, and wrong versus correct for firing and demo. If you remember only three sentences, park the connection, fire on size or timeout, demo by position. Then add option C when they ask how it scales. You now have a story you can tell in 5 minutes or 45. Same bones. Depth is optional, clarity is not. Carry these probes into practice. What if traffic is tiny at night? What if a slot fails inside a batch? What if the batcher CPU saturates? Your answers are timeout floors, positional status, and gateway partitioning. Your Ally AI at yourally.live is where you can rehearse those probes until they feel boring. And boring is the goal.